Hello guys, I want to welcome you to homework 8. It says the moon is 3.85 times 10 to the 8 meters from the earth and has a diameter of 3.48 times 10 to the 6. So we have the earth here, we have the moon here. So as you are looking at the moon from the earth, so you are given the diameter of the moon and the distance. So we're going to take this distance as a radius and this diameter as like S and R. Is that okay? So these are our theta, like our angular view. So theta is S over R. So for the moon, the angular view, S over R, is going to be the diameter of the moon, 3.48 times 10 to the 6, divided by R, 3.85 times 10 to the 8. This will give you about 0.009 or so. Okay, now let's compare this to holding your arm's length out 71 centimeters, that is your new R, and having a P of diameter 0.5. So let's calculate theta for P. So it will be S over R. S this time for P is 0.5, and R is the arm's length distance, 71. So I'm working both in centimeters, so I can convert both to meters too. This will give us about 0.007. So this is smaller than that, so this guy cannot cover that angular view. So let's do for the dime. Theta for the dime is S over R. The S now is 1.8 divided by 71. This will give us about I think 0.9 something. Okay, so let's check that out. I think 0.07 something. Well, let's make sure. So let me start from the beginning. For the first one, 3.48 divided by 385. 0.009, correct? Then for the second one, 0.5 divided by 71, 0.007. Then from now, 1.8 divided by 71, 0.025. So it's 1.8 divided by 71. 0.025. So 0.03 approximately. So 0.03 is bigger than 0.009. So this will cover that. That will completely, as you see that. So that will completely cover your view of the moon if you hold that over the moon. So it's going to be the dime, and that's why the correct answer is D, because it has a wide angular view right here. Okay, let's go to the next problem. It says a rotating object has an angular acceleration alpha that is not 0. That's focused on concept question 05. Which one or more of the following three statements is consistent with a non-zero acceleration? So when you have a non-zero angular acceleration, so it means your angular velocity increases as time passes. That is the only way you can have angular acceleration. You don't have a constant angular velocity. Your angular velocity is changing. The angular velocity has the same value. No, that's wrong. That means constant angular velocity, then you will not have angular acceleration. You can still have centripetal acceleration, but you cannot have angular acceleration because you have a constant angular velocity. Then the angular velocity decreases. That is also possible. So A and C is correct, but not B. So the correct answer will be 4 right there, A and C, but not B. Okay. Okay, the next problem says, Chapter 8, Problem 1, a pitcher throws a curved ball that reaches the catcher in 0.353 seconds. The ball curves because it's spinning at an angular velocity of that, 250 revolutions per minute. What is the angular displacement? So we know that angular displacement divided by time is angular velocity. So angular displacement is angular velocity times time. Angular velocity is given to be 250 revolutions per minute. That's 250 times 2 pi divided by times 60. So let's do that conversion. So we need to convert revolutions per minute to radians per second. So it is 250 revolutions per minute times 2 pi radians is 1 revolution, so revolution cancel revolutions, times 1 minute is 60 seconds. So seconds cancel, a minute cancel minute. So I have radians per second left. Then times time, the time given is 0.53. So when I multiply all that, 250 times 2 pi divided by 60 times 0.53, that will give me my angular displacement. So 250 times 2 times 3.142 divided by 60 times 0.53, 13.9 radians. 13.9 radians. So that is my theta in radians, okay? So working in radians, you have to change your speed, your angular speed to radians per second before you do the problem. The Earth spins on its axis once a day and orbits the Sun once a year. So determine the average angular velocity in radians per second. So this is really simple. 1 revolution, which is 2 pi radians, divided by, for a day, the spin on its axis. So spinning the axis is the 24 hours, so that's 24 hours. And the other one is the 365.25. Is that okay? So for question problem, chapter 8, problem 3, we want to get the angular speed of the Earth as it rotates. So theta over time is omega. So 2 pi for 1 rotation for 24 hours for the spinning for the A part. 24 hours times 3,600 seconds is 1 hour. So just 2 pi divided by 24 times 3,600. That'll give you that. So I have 2 times 3.142 divided by 24 divided by 3,600. So it gives us 7.3 exponential minus 5, actually, not minus 4. Okay. So it's 7.3 exponential minus 5 times 10 to the power minus 5 radians per second. Then for the B part is the same, 2 pi, but this time around divided by 365.25 days. So you have to convert this to seconds times 24 hours is 1 day, day cancel day, times 3,600 seconds is 1 hour, hour cancels hour. So 2 pi divided by this times that, okay? So let's see what that gives us. So that gives us 2 pi, 2 times 3.142 divided by 365.25 divided by 24 divided by 3,600. 1.99 exponential minus 7. So that's correct. So 1.99 times 10 to the power minus 7 radians per second. So that solves the problem. So it's just the conversion of these to seconds. The different one for spinning about the axis and for moving around the sun, the different times is what gives the different angular velocities. Okay, let's go to the next problem. So the next problem says the rotating wheel has a constant angular acceleration. It has an angular velocity of that at time t equals 0, and 3 seconds later it has an angular velocity of that. What is the angular displacement of the wheel during the 3 seconds interval? So we have the initial and final angular velocity, so we can get the acceleration. So acceleration is, you don't even need that. So you can even use this formula. You don't need to get the acceleration first. We can just get theta directly. Is omega final plus omega initial over 2 times t. That's it. So it is 5 plus 9 divided by 2. That's average velocity times time times 3. So 9 plus 5 is 14 divided by 2 is 7 times 3, 21 radians. And that's the correct answer right there. Or you can find the acceleration first and use other kinematic equations to find the distance or the displacement, but that's too long. You are in a tall building located near the equator. As you ride on an elevator from the ground floor to the top floor, your tangential speed due to the Earth's rotation increases. Why? Because you are near the equator. So when you are near the equator, V is omega R. So let's see what happens in that problem. That's focus question 09. Sorry, I didn't make it large enough. For some reason, I don't know what happened while I was editing this. Let me see if I can make it large enough now for you guys to see. Let's get that. If you guys can see this problem large enough. Okay, let's hope this is better. So it's a little larger. So you're in a tall building near the equator. So the Earth is somewhat like an egg-shaped thing like that. So the equator is right here. So your radius from the top to the pole and the radius to the equator, R equator. So R equator is greater than R pole. So and V tangential is omega R. So the larger the R, the larger the tangential speed. So that is the trick. So when you're around the equator and you're moving in a circle, your tangential speed will be more than when you are close to the poles, okay? So your tangential speed due to the Earth's rotation is gonna increase. Okay. Next problem. A small fan has blades that have radius of 0.06 meters. So R is 0.06 meters. When the fan is turned on, the tips of the blades have a tangential acceleration. So we have A tangential is 12.5 meters per second squared. Don't forget the formulas we use are S is R theta, linear displacement, radius times angular displacement. V is R omega, linear velocity is radius times angular velocity. You just get this by dividing this one by time. Linear distance over time, linear velocity, angular displacement over time, angular velocity. If you divide this by time again, linear acceleration, V divided by time is radius times omega over time, angular acceleration. So these are the three formulas basically we've been playing around with, apart from the kinematic equation ones that you have. So we have that tangential acceleration. What is the angular acceleration? So we're looking for alpha. So you see alpha is A over R, tangential over R, 12.5 divided by 0.06. And if you do that, you're just going to get that 208.33 radians per second squared. Okay, that becomes the answer. So the next problem, question 13, says, sorry. A wheel rotates with a constant angular velocity. Which one of the following is concerning the angular acceleration of the wheel? The tangential acceleration at the point on the rim of the wheel and the centripetal acceleration of the point of the rim. So they gave various options right there, but be careful. Once you have a constant angular speed, you cannot have an angular acceleration. So your angular acceleration will be 0, and once you have an angular acceleration of 0, you're going to have a tangential acceleration of 0. So if alpha is 0, A will be 0 for sure. And then the only thing you're going to have is the centripetal one. Centripetal one is the only one that will not be 0, because you have tangential velocity. Is that okay? You have tangential velocity. And it is the changing tangential velocity that gives the centripetal acceleration. So if you're going in a circle, your omega and alpha are around the circle, but your V and A tangential go like this, and centripetal is always towards the center of the circle. Is that okay? So once you don't have alpha, you can't have A tangential, but because you have V tangential, that is the one that gives this acceleration towards the center of the circle. Okay, so that's the correct answer. Alpha 0 because omega is not changing. Omega is omega final minus omega initial over time is alpha. So if you have a constant omega, you have 0 change, so you're going to have 0 alpha. And once you have 0 alpha, you have 0 A. So the only acceleration you're going to have is centripetal. Okay, next problem. The radius of each wheel on a bicycle is 0.4 meters. That's question 15, focus on concept. The bicycle travels a distance of 3 kilometers. Assuming that the wheels do not slip, how many revolutions does each wheel make? So you want to convert the distance to revolutions. Is that okay? So we have S, we have R, we have theta. So R is 0.4. So we are looking for theta. And S is R theta, okay? So we're going to convert linear displacement to angular displacement. That is just the problem right here. So linear displacement is 3 kilometers. 3,000 meters is R times angular displacement, R theta. So this is your S, is R theta. So R is 0.4 times theta. So theta is 3,000 divided by 0.4. That's 30,000 divided by 4. Okay. 2, 15, 2, 7.5, 7,500. Okay. So I have 7,500. Let me see. 15 divided by 2. Yep. So if I times this by 4, I'm going to get 30,000. So this one is in radians, but they want it in revolutions. So in revolutions, I convert radians to revolutions. So it becomes 7,500 times 1 revolution is 2 pi radians. So that radians cancel radians. So 7,500 divided by 2 pi will give us the answer. So 7,500 divided by 2 divided by 3.142, 1,193. So to the nearest revolutions, it's almost 1,193. To the nearest is 1,200 revolutions. But if they want the exact number, is 1,193. But 1,200 is the when you round it up to a whole number, okay, or to the nearest 100. So each tire on a car has a radius of that and is rotating with an angular speed of 11.7 revolutions per second. Find the linear speed. So we are given the angular speed. So V is R omega. So we are given the radius 0.33. Omega is 11.7 revolutions per second. So 11.7 times 2 pi radians to get radians per second. So if I do this multiplication, I'll get my linear speed. So 0.33 times 11.7 times 2 pi. .3 meters per second. That solves the problem. So just convert your omega to revolutions per second. 2 pi radians is 1 revolution, and you cancel revolution, and then you get that times 2 pi. Okay, that's how you work with the SI units. So we'll go to the next problem. So it says a Ferris wheel rotates at an angular velocity of that. So we are given omega, angular velocity. So let me wipe off most of the board to solve this problem. So our angular velocity omega is 0.21 radians per second. Starting from rest, so omega initial is 0. Okay, it reaches this operating speed at an average angular acceleration. So I have alpha as 0.028 radians per second squared. How long does it take the wheel to come to this operating speed? So they're looking for time. So I know alpha is omega final minus omega initial over time. So what is time? Omega final minus omega initial over alpha. So that just solves it. 0.21 minus 0 over 0.028. That's it. So 0.21 over that, that'll give us the 7.5 seconds. So let's prove that. Let's confirm that. That 0.21 divided by 0.028. 7.5 seconds, correct. Next question, problem 38, chapter 8. A fisherman is reeling in a fish. In 8.5 seconds, he winds 1.4 meters of fish line onto a reel. Whose radius is that? So we have the radius and we have the tangential displacement. So we can get the, what do you call it? The tangential speed. Is that okay? So you move this distance in this time. So what's your V tangential? It's just distance over time. 1.4 over 8.5. That'll give us our V tangential. So 1.4 divided by 8.5, 0.165. 0.165 meters per second. But they're asking us to find angular speed. So V tangential is radius times angular speed. So angular speed is V tangential over radius. 0.165 over the radius is given to be 3.4 centimeters, 0.034 meters. So 0.165 divided by 0.034 gives the answer. Okay? 4.844 exactly radians per second. So we'll have 4.84 radians per second. That's the angular velocity. Okay, then we'll have the next problem, chapter 8, problem 48. In a fast-pitch softball game, the pitcher is impressive to watch as she delivers a pitch by rapidly whirling her arm around so that the ball in her hand moves in a circle. In one instance, the radius of the circle is that. At one point on this circle, the ball has an angular acceleration of that and an angular speed of that. Find the magnitude of the total acceleration, centripetal plus tangential. So we'll have, so I'll have to draw this diagram for you guys to see what's going on here. It's a very interesting problem. So we are going around this circle. So you have your A centripetal, you have your A tangential, okay? So they want us to find a net A. So the A tangential is R times alpha, so let's get that. The R, the radius of the circle, 0.656 times alpha is given to be 67.3 radians per second squared. So this gives us our A tangential, okay? 0.656 times 67.3, 44.15 meters per second squared. Now let's get our A centripetal. So we are given the angular speed. So A centripetal is V squared over R or omega squared R. They are both the same. Since we have angular speed, I don't need to find V. I can just use this. But even if I calculate V first and use this, I'll get the same answer. So I've just used the omega. I'm giving 13.4 squared times 0.656, the radius, okay? So 0.656 times 13.4 squared, 13.4 squared times 0.656, 117.79 meters per second squared. That's my centripetal acceleration. So what is my net acceleration? Total acceleration, A net. So A net equals A tangential plus A centripetal squared each square root. 117.79 squared plus 44.15 squared, all square root. That becomes my net. And they need the angle to the radial side, theta. So let's get the net first. 117.79 squared plus 44.15 squared is that. Let's take square root of that. 125.79. 125.8. That's the correct answer there. 0.8 meters per second squared. So now let's get the angle theta. So theta will be tan inverse of, because tan theta is opposite, A tangential over A centripetal. So that's the tan inverse of A tangential 44.15 divided by A centripetal 117.79. So if you divide this, take the shift tan of that. Let's see if that gives us 20.5 degrees. So I'll do 44.15 divided by 117.79. Take the shift tan of the answer I just got. 20.5 degrees. Perfect. So that's the answer. They want the acceleration angle relative to the radial direction. This is the radial direction, the radius direction. Okay, if they wanted the angle relative to the tangent direction, we'll get the other one, which is 90 minus this one. So this just gives us 20.5 degrees. Okay, the last problem, problem 56 of chapter 8. Suppose you are riding a stationary exercise bicycle and the electronic meter indicates that the wheel is rotating at 11 radians per second. The wheel has a radius of that. If you ride for this time, how far would you have gone if the bike could move? So they're looking for distance. Okay, so let's go. So we can't get distance directly, but we can get what is it called? The theta, the number of rotations. Then from the number of rotations, we get the distance. So that's one way to do it. Or you want to get your speed and then use the kinematic equation. So your choice. You get the same answer, however, whichever direction you take. So I know that I'm looking for distance. I'm giving omega. So we have time and omega. Okay. Okay, so you have a steady speed. So you're moving at a steady speed for a particular time. Okay. So displacement over time is speed. So displacement is omega times time. That's all. So omega is 11 radians per second times the time 39.8 minutes. So that's 39.8 times 60 to get to seconds. So when I do this, 11 times 39.8 times 60, I see what it gives me. 11 times 39.8 times 60, 26,268. So this is radians. So, but this is, I need S, the distance, linear displacement corresponding to this radians. So it will be the radius, which is given to be 0.38 times this 26,268. Okay? So the answer I just got times 0.38. 9,981. 9,981.84. Exactly meters. So it's converting the theta to S, and that's it. And that solves the problem. So that marks the end of the recitation. I mean the homework 8, and I'll see you guys for homework 9. Have a good one, guys.